Bonjour from Montreal, where we really wish you were here visiting this week. I want to thank Taryn, Alex, and Nick for inviting me to speak today. I'll be presenting work by my former master's students, Kat Ross, who is now at UT Austin, and Sam Mateer, who is currently finding gold and pseudotachylites in northern Manitoba. Different scientific methods or approaches result in diverse views of faults and shear zones. To reproduce observed fault motions and generate the earthquake cycle in mathematical models, spatially and temporally varying rock strength and changes in deformation behavior are needed. However, these models cannot reveal the deformation mechanisms which cause this behavior. Field mapping and exhumed faults and shear zones shows evidence for numerous brittle and plastic mechanisms which may act simultaneously. How then to resolve these two ways of understanding faults into a coherent paradigm? Classical view of shear stress during the earthquake cycle hasn't actually changed much since Reed proposed elastic rebound theory inspired by the 1906 San Francisco earthquake. Stress can't be measured directly on a fault, but our ability to detect changes in stress has increased significantly. Now that we have source time functions for the CO-SEISMIC period, we know that slip acceleration and velocity vary during earthquakes, which could be due to rupture geometry complexity and strength variability on the fault surface. These cannot be distinguished from seismic data alone. We can also better resolve aftershock cycles and geodetic evidence of progressive fault locking. Gradual and punctuated afterslip can be observed in surface displacements if it is sufficiently large. With gradual locking, the fault begins to reload for the next earthquake. It is not possible to see from the surface which mechanisms in the rocks in the fault zone cause transient and local changes in strength and stress during deformation. Our view of fault zones, conversely, seems to have oversimplified as a side effect of the need for simplification for modeling purposes. Exhumed shear zones contain numerous seismic slip surfaces, and our research shows that it's common for several parallel surfaces to slip together in the same event. Tools to detect past seismic slip are only useful on sharp localized surfaces because they rely on frictional heating, so there may be thicker rupture surfaces we cannot currently find. Earthquake models have traditionally imagined the surrounding wall rock as elastic, but we know it is at least partially plastic because exhumed examples show distributed, intense deformation fabrics like foliations and scaly fabrics, and zones that may be at least as wide, if not wider, than the zone of seismic rupture surfaces. In the seismogenic zone and the lower transition zone, these fabrics form by dislocation creep and solution creep, which act at the same time. Here's an example of one such zone. This is the exhumed approximately 900 million year old Pelfatter shear zone in South Africa. The fault core here is about 15 to 20 meters wide of ultramyelinite zone containing countless pseudotachylites. This is surrounded by a region of intense parallel foliation, almost 50 kilometers wide, which records part of the shear zone's budget of strain both along and across strike. Faults are also surrounded by a compliant damage zone of fractures. Fracturing happens during slip at all depths, but fractures heal more quickly within and below the seismogenic zone, so fracture damage zones are most persistent in the shallow crust. The properties of this zone may evolve as fractures close over time in between earthquakes at depth-dependent rates. Recent models can incorporate the viscosity of wall rock. Ironically, they can produce very similar earthquake cycles, according to what we would see at the surface, but the stress and loading patterns and the deformation mechanisms at depth are quite different. Every one of these components of the fault zones is a participant in each stage of the earthquake cycle and responds to stress changes on the fault. Any one of these components, or more than one of them, could be the source for the movements and seismic waves that we detect from the surface. Luckily, exhumed shear zones offer us an insight into the mechanics of these deep structures. I'm about to show you a little bit of recent progress in understanding how these structures contribute to the overall fault zone behavior. These famous outcrops of the NORUMBEGA shear zone in Fort Foster, Maine, USA, showcase structures that demonstrate off-fault deformation contributing to the overall displacement during and after earthquakes. Here, a 19-meter wide zone of ultramyelinites with color banding, compositional banding on scales of about a millimeter are shot through and offset by numerous pseudotachylites. These are solidified melt layers that record frictional heating on the slip surfaces of ancient earthquakes. Many years ago, Mark Swanson discovered pseudotachyllite-filled fault-adjacent voids. These are produced by slip on the very same fault that produces the pseudotachyllite. The pseudotachyllite injection filling the center of a box fold formed during fault parallel shortening of the upper block during slip on the white fault. The myelinite fabric kinked to produce a void in the core of the box fold, which was filled by draining of pseudotactylite melt from the slip surface. Since the quench time of the pseudotactylite this thin is thousandths of a second in conductive cooling models, the box fold must have formed during earthquake slip. Catherine Ross took this concept a step further with her study of two subparallel pseudotactylite veins formed in the same earthquake. The pseudotactylite faults are wavy and are joined by tensile cracks filled with mixed pseudotactylite from both ends. So when both slipped, at an approximately magnitude 6 earthquake, this would have created space problems in the wall rock due to mismatch between the shifting sides of the fault. This caused a heterogeneous distribution of stress changes after the slip. Catherine mapped every tiny structural feature that deformed or offset the myelinitic foliation between and around the faults. This included pseudotactylite injection veins emanating from the pseudotactylite faults themselves, sets of microfaults with apparent displacements as small as 100 microns, and the folds and kinks that deflect the foliation. Catherine's maps record pre, co, and post-seismic deformation features, so she devised a way to test which ones were related to the slip on the faults. Those features containing pseudotactylite from the faults are clearly co-seismic, and for the others, she was able to test for kinematic consistency with Coulomb stress changes caused by the co-seismic slip. Using Coulomb 3 for MATLAB, Catherine input the fault geometries from careful field mapping and imposed displacements constrained by offset markers. She tested the clearly co-seismic features, the pseudotactylite injection veins, represented by triangles, to see if they occurred in areas where the fault offset would have caused stress changes that encouraged opening mode fracturing in the rock, the redder areas in the model. The agreement is good, but not perfect, suggesting that either the 3D fault geometry we couldn't measure on the outcrop surface, or the co-seismic dynamic stresses also played a role in controlling the location of injection veins. The small faults are a little more ambiguous. They sometimes correlate with locations of significant stress change, but not always. Some of the faults may have been caused by the dynamic stresses, or they could have localized on pre-existing structures. Or some of them may not be associated with these earthquakes at all. But many of them, and clusters of them, line up well with the regions of predicted high stress change during the earthquake. This is effectively a direct observation of co-seismic off-fault fracturing, a miniature model of seismic damage to wall rocks, resulting in bulk wall rock compliance. Sam Mateer's work investigated the post-seismic ductile deformation of pseudotactylites in their host rocks. The Fort Posture ultramyelinites are rife with pseudotactylites at gradual stages of recycling, that is, being sheared out into the surrounding ductile layering. Here, a fresh pseudotactylite injection vein intruded a small fault which cuts across older layers. Several more small faults at the same location may have slipped in the same earthquake, but they were not connected to the pseudotactylite source fault. The yellow arrows point to partially myelinitized older pseudotactylites. These lie along myelinitized quartz veins, with whom they share the deformation fabric, showing that they were co-deformed after the earthquake that formed the pseudotactylite. Sam searched for examples of coupled quartz veins and pseudotactylites to see if the flow stress in the quartz layers, which we could estimate using paleopiezometry techniques, could be used to constrain the post-seismic strength of pseudotactylite. He made two observations that suggest that the quartz and pseudotactylite deformed together with negligible strength contrast between them. One, the planar layers with smooth contacts between them show that both layers could flow without a discontinuity between them. Second, since deforming layers of different viscous strengths result in boudinage, Sam was able to test for pinch and swell geometries using a suite of long-range measurements. The lack of measurable pinch and swell undulations over many measurements of coupled pseudotactylite and quartz veins argues that their strengths were matching. There is little laboratory data available that would allow us to estimate the viscous strength of the pseudotactylite after the earthquake. The component minerals, micas, epidote, amphibole, and feldspar, are not terribly well constrained from laboratory experiments, and the mixture, fine-grained mixture of these minerals is not at all well described. The grain size of the quartz ultramyelinite layers coupled with pseudotactylites was 10.5 to 11.5 microns. Depending on which paleopiezometry you choose to use, this grain size suggests a flow stress of 75 to 95 MPa during deformation. Sam measured the same grain size in quartz ultramyelinite layers of different generations, like the foliation parallel band, area B, and a small cross-cutting shear, area C, and found identical mean grain sizes, suggesting that the shear stress stayed in this range through an extended period of time. The crystallographic preferred orientation SAM measured are consistent with dislocation creep in regime 2 in quartz in the myelinitic quartz ribbon layers, layer B. The tiny offset, which dragged and reworked the quartz layer, shows microstructure consistent with grain boundary migration and prism A slip. Assuming that temperatures had stayed constant between these two deformations, this probably means that the creep rate had slowed down by the time shear C deformed myelinite layer B. The rocks of Fort Foster display the rock record of co-seismic complexity, including non-planar, multi-stranded, intersecting rupture surfaces. The natural consequence of this roughness is spatial and temporal variation in strength, which creates a feedback with frictional heating, which in turn controls strength. Pseudotactylite recycling develops through crystal growth, leading to dynamic recrystallization. Coarsening apparently stops when the effective strength of the different layers in the myelinite becomes similar, even if they are deforming by different deformation mechanisms. The shear zone then creeps slowly at high stress, locking in the CPO we observe by EBSD until the stress is high enough to trigger rupture through the network again. So to conclude, we've shown that on and off fault deformation go hand in hand at all stages of the earthquake cycle. A variety of deformation mechanisms might be responsible for the patterns of deformation we see from the surface, which aren't well described by traditional friction models, even if those can be tuned to match the patterns. There is still a lot we have to learn about fault locking in particular, which is hard to harmonize with viscous fault zones susceptible to solution creep and crystal plasticity. Thank you very much.